Okay, good morning. So I think it is a good idea if we can wait a little bit for others to arrive if they are coming. But in the meanwhile, might be it is a good idea that you can, of course, this is one of those exercises. I didn't do it, but that would be a good idea if you start doing this by for refreshing up your memory and waiting for others a little bit, and then we go to the new lesson, which I will talk about logical equivalence today. Okay, so
Didn't we do this one last time?
we didn't do that. I said that uh, we talked about it, but we didn't do it properly. But that's why I'm saying that if you want, you can do it now, and then we can continue. Okay? So we want to show that this is a contradiction. It means that we should show that for any assignment for P and Q, truth value P and Q, it doesn't matter. At the end of the day, it becomes always false. That's the meaning of a contradiction. What was the other extreme? What the name? Tautology. Yeah, so tautology is the other one, which is always true. Okay, so I would recommend you to try to refresh your memory a little bit by doing this exercise for 2 or 3 minutes, and then we will continue to the lesson today. Okay, so let us do this one here just for a warm up, and then we go to the new lesson. So we want to show that this is a contradiction. So P and Q, P or Q, and then the other one is and. So let me use the convention. Do you remember what was the convention? So here I really don't need to put another extra pair of brackets because we said that this negation will apply as little as possible. Yes? So let me write it in this way from now. So we want to show that this is a contradiction. So I need, for the time being, the only way we can do it is set up the table. Okay? So how many atomic prepositions are there? 2. So P and Q. So there are 2 to power 2 rows. So it means 4. So I would write P and Q. So I will have T, T, F, F. And I will have T, F, T, F. These are the old possibilities, but I have to construct it little by little. And the order does not matter that much, of course. For example, I can put P or Q here. Yes, I hope that you have it in your memory by now. Of course, this is logic. You don't really, in principle, need to memorize anything, but it's good to have it. So T is T. T or F is T. F or T is also T, but F or F is. So the next stage is I need not P. So not P is exactly the opposite of P. So we have 2 T's here, so it starts with 2 F's. And when you have 2 F's, it will go with 2 T's. And then I also have not Q. This is opposite to this one. So T becomes F, F becomes T, T becomes F, F becomes T. And then I also need the conjunction between these two. So not P and not Q. So F and F is F, F and T is F, T and F is F, and then T and T is T. Yes? This is, and then finally the whole expression. Okay, so the whole expression. So what is that? I need to have the conjunction between this column and that column. So T and F is F, T and F is again F, T and F is again F, F and T is again F. And you see that the last column consists of only F's. So this means that this preposition, it's a compound preposition, it's a contradiction because it always is false. Any questions? Okay, so this is a good definition. Let us stick to it. So a prepositional sentence when I say I have a prepositional sentence, I mean either I have a compound sentence or just a component. Yes. So for example, here I can say that, okay, if I have only one single preposition, I call it atomic preposition or a component, but still I can also consider it as a prepositional sentence. Even if I have a compound preposition, I can also call it a prepositional sentence. So when I say a prepositional sentence, I mean either one preposition alone or a compound preposition. These are the terminologies that good to know about them, okay? So this is the main topic for today's lesson. So let psi and phi, and I will stick to this convention. For example, for atomic ones, I use English alphabet, P, Q, and R. And then if I use Greek letters like psi or phi or I don't know, alpha or something like that, I mean a prepositional sentence. Of course, a prepositional sentence, as I told you, can also be a atomic preposition, but usually when I use psi, phi, alpha, Greek letters, I mean compound prepositional sentences. Yes? Okay. So there is a difference. What I'm saying is that there is a difference. If in my lessons you see I am writing psi, I mean might be this is not atomic one. It might have an internal structure. Yes. For example, this one I can call it psi, for example. Yes, something like that. Okay, so now let psi and phi be prepositional sentences. We say psi and phi are logically equivalent and write this symbol, this notation that you see, psi, this double-sided arrow, phi. Or I myself prefer to use this notation, psi with 3 horizontal lines, equivalent, logically equivalent to phi. I will use this. If for every truth assignment applied to the components of psi and phi, the resulting truth values of psi and phi are identical. In this case, this relation that you see is called a logic law. Yes? Yeah, is that clear? So, two prepositional sentences are said to be equivalent if for every assignment of truth or falsity to the components for psi and do the same assignment for phi, they become the same. Yes, that's the meaning. Okay, for example, let us show that this is a logical equivalency. It's a logical law. So I want to say that if P then R and if Q then R is equivalent to saying P or Q then R. Okay, so let me write it down here. So we want to show that this P, if P then Q and if Q then R is equivalent to if P or Q then R. Yes. By the way, is that a little bit understandable? Yes. You say that P is a sufficient is a sufficient condition for Q. That's also P. Yes, that's P. Thank you.
No, it's P then R. And then
so this is R. Yeah, sorry. This is R. This is Q. Yes. If P then R and if Q then R. Yes. And then we say that if P or Q, either P or Q then R. Yes, we want to show that these two things are equivalent. From later, we want to talk about algebra of prepositions. So in principle, this seems like a factorization. So you are taking arrow R, factoring it out from the right. But this is not something like distribution here. because distribution happens if this will be the same, but it is not the same. So it means that if you take this arrow to the right, out from the right hand side, if you factor it out from the right hand side, then this becomes P or Q. If we can prove it. Okay, if I want to prove that this is the case, I need a little bit long table to, but I don't want to have two tables. I want to have one big table containing this and that together, and then compare them column-wise. Okay, so let us do that. So for this one, by the way, how many? Oh, I need a big one. So let me. Okay, I think I can fit it here. So how many rows I need? 8, because I have 3 atomic prepositions, P, Q, and R. So 2 to power 3 is 8. So I need 8 rows. Okay, so I have to be a little bit careful here to fit everything here. So P, Q, R. Yes. Let me see if I'm recording or not here. Okay, so do you remember how should I arrange them? What was the algorithm? So 8 divided by 2, 4. So I will start with 4 T's and then 4 F's. The next column, I start with 2 T's, 2 F's. Yes, and the next one, 1 T, 1 F, alternatingly. And please also check my calculations. TF, 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 TF. Okay, then what do you think I will need next? Of course, order is not that important. Sometimes order matters, but it's not that strictly. So what do you think I will write here?
P then.
If P then Q, it's conditional. Sorry, P, if P then R. Okay, so do you remember a conditional is false if and only if the premise is true, but the conclusion is false. In other words, the left side true, the right side false, it becomes false. Otherwise, it is true. So in this case, I have a conditional between P and R. T, T is T, but TF is F, T, T is T, TF is again F, FT is T, 2 F's again T, FT is what? T, and 2 F's is T. I also need another conditional if Q then R. But this time I concentrate on these 2 columns. T, T, so that is T, TF, it is F, FT is T, FF, T, T, F, T, and T. Yes? Do you agree? And then, of course, I need the left-hand side. So let me not write everything. So the left-hand side, this is the preposition on the left-hand side. And I want to have the conjunction between these 2 columns. Yes? So T and T, T, this is F, this is T, this is F, T, F, T, and T. So the left hand side is done. And then I go to the right hand side. For the right hand side, I need P or Q first. So I go and look at the first 2 columns. I want to have the disjunction between these 2 columns. So T or T is T, and this is T, and this is T still because that's OR. This is also T, this is also T, this is T, this is F, and this is also F. Okay, so now the exciting moment is here that we haven't messed up, hopefully. So that is the right hand side now. because be careful this time. P or Q is on the right side, on the left side, R is on the right. So this is your premise, this is your conclusion. Okay, so T, and then I have to concentrate between these two. T, then T. If T, then T is T. If T, then F, which is false. T and T, it is T. T and F is again false. T and T is T. T and F is again false. F and T is T. F and F is T. Are we relieved or not? Yes. Because if you compare these two, they are identical. So it means that whenever the left-hand side is true, this case, yes. So this means that whenever the left-hand side is true, the right-hand side is true. Also, whenever the left-hand side is false, the right-hand side is also false. So this is a logical law. So it doesn't matter if you say this sentence, prepositional sentence, or that prepositional sentence. Yes? So for example, I can say that I know this is not a preposition, but I want to just give you a feeling. So let us say P is, X is the square root of 3. Yes. So let us say that P, B. Of course, this is not a preposition. Yes. Because we don't know if this is true or false. But let us try to just ignore that part. So P, X is equal to square root of 3. Let me write. And then Q, let me write X is equal to square root of 2. And then let me write R is, X is irrational. Okay, for example, you say that if X is equal to square root of 3, then X is irrational. And if X is equal to a square root of 2, then X is irrational. You can equivalently say that if X is equal to a square root of 3, or if X is equal to a square root of 2, then R is irrational. So we have shown that these two sentences, prepositional sentences, are equivalent. And for all cases, I'm just giving you a feeling how it looks like. Yes?
But, so for example, in this case, X equals square root of 3 and X equals square root of 2.
Yeah?
Can both of those statements be true at the same time?
No, it doesn't matter. That's the whole point. That doesn't matter if these statements are true or false. This means that the left-hand side is always equal to the right-hand side. You have to get used to it in logic, yes?
Yeah, but it's more like when you're saying.
First of all, this is not a statement.
No.
Because X equals to the square root of 3 is neither true or false. It depends on what you assign to X. Yes.
But the way you read it, I mean, it makes sense like in a sentence, like if X equals square root of 3, then it's irrational, and if X equals square root of 2.
So this might be easier. If P is a sufficient condition for R, so let us say R is something that we have two sufficient conditions for it to occur.
Yeah.
Yes. So I would say that if P and Q, okay, are both necessary conditions for, both sufficient conditions for R, meaning that if I grant you P, you can conclude Q, you can conclude R, and if I grant you Q, you can also conclude R. It's logically trivial that if I grant you either P or Q, you can still grant me R. Yes? Well, that's the more or less the meaning. Yes? Of course, yeah, that's why I'm saying I want you to rely mostly because, for example, if we are doing mathematics, this is somehow in the back of your head without really checking the truth. So this is useful for very complicated sentences, especially if you're writing a coding and programming or something like that. If the sentence is very complicated, might be it is not easy for us to understand it intuitively. We have to do a little bit more precise calculations. But anyway, we don't have this necessity that it should be meaningful. The definition of logical equivalence is this. So they are logically equivalent. Is that okay? Okay, now I want to go to another example. I want to wait a little bit for you. Are the statements P, this statement that you see here, and this statement logically equivalent? Motivate your answer. Okay. Okay, so what do you think? Are they logically equivalent or not?
Do not.
They are not. So if you say they are not, you have two, you can do it in two different ways. Completely find the totality of this by the table and see that they are not identical, or if you are good enough, you can just calculate it in your head. You can find an assignment, any specific assignment for PQ, so that for those assignments, the left-hand side and the right-hand side does not match. If you can come up with that idea, that is quite okay. Okay, but if you cannot, if it is complicated, you can just draw the table for the left side and the right-hand side and see that they are not identical. Yes. So for example, here, I can, if I want to do it through the table, so I would write P and Q only. So I have only two T's first and two F's here. And then I have TF, TF. And then I need what? I need not P. So it becomes FF, TT. And then I will have Q and not P. So Q and not P are these two. So it is F, F, T, F. And then finally I have the left-hand side. So the left-hand side is OR between these two columns. So this is T, this is T, this is T, and this is F. And for the right-hand side, I need P or Q. So P or Q is T between these two. This is T, this is T, this is F. And then finally, I need the right-hand side. So the right-hand side is the AND between this column and that column. So this becomes F, this becomes F, this becomes T, and this becomes F. Okay, and then I compare the right-hand side with the left-hand side. Are they equivalent? Clearly not. Yes, because here, for example, we have a T, but here we have a F. Here we have a T, we have a. So they are not identical. So they are not logically equivalent. Okay, so that is not hard. But the interesting part of today's lesson is a lot of formulas, logical laws that I want you to know by heart somehow, which will enable us to actually check the equivalency like algebraic calculations rather than drawing the tables. But we have to set up. There are a lot of these. I can show you the list. I will show you the list. But before that, I want to ask your opinion about it because there are a lot of them. I want you to memorize them, yes, and I want to ask your opinion about this. For example, the first law is the law of double negation, yes. So the first law, it's called the double negation. I will not write this down because I have the PDF file and you will find it below the video. But here, negation of a statement, of a proposition. What do you think it will be? It is equivalent to what? It is equivalent to P itself. Okay, so that's nothing to memorize here. So what do you think about this? If I take a preposition and have the conjunction of that preposition with itself, can I simplify it a little bit more here? P itself, yes, it seems so. But of course, if someone asks you to prove it, how do you prove it? For example, how do you prove this one? You need to write a table. How many rows I need? No, two, because I have one atomic preposition. So 2 to power 1, 2 rows. So it means that I have P, T, and F. Okay, so P again is T and F. And then of course P and P becomes what? T, 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 F, F, F. And then you compare this one with that one, they are identical. So the proof for these, we have to use the table, yes? But after we use the table to prove them once, we can always use them for the proof. And then of course, do you think we also have something like this? Or, yes, P or P is also equivalent to P. These are called idempotent laws. Yes. So we have two other laws. So P and a contradiction. You remember this symbol was used for contradiction. So what do you think will be P and a contradiction? It should be a contradiction. Yes, because it doesn't matter P is true or false. Whenever you do that, it becomes a contradiction. So that is called the contradiction law. Do I have something which I can call a tautology law? Not for and, but we can have it for or. Yes, so we can say number 4, this is called the tautology law. So it means if I take any preposition and I have the disjunction of that preposition with the tautology, it becomes what? A tautology. Independent of the truth value of P. Okay, so do you see that you don't really need to memorize them, but it is used, we need them, okay? So number 5, so what do you think about this combination? It's a contradiction. So the door is open and the door is closed. Simultaneously, this cannot happen. So this is a contradiction. So this is equivalent to a contradiction. And that is called complement laws because we have 2 of them. Can you guess what is the other one for or? So P or not P is a tautology, yes? Immediately you can see that the door is open or closed. So it's always true, either the door is open or closed, something like that. Okay, so number 6, if this is now P2 prepositions involved. The first thing is that this is commutative. So it doesn't matter if you write P and Q or Q and P. They are equivalent. We also have the same for or. These are commutative laws. But I told you an example last time. Do you remember? I went to the doctor and I became sick. I went to the doctor. in English, if you change it, I went to the doctor and I became sick. This is probably not equivalent when you see it. But anyway, logically they are equivalent. If someone asks you why, how do you answer again? You have to draw a table for the left side, the right side, and compare it. And then, of course, it is completely clear that they are the same. So these words are very famous in mathematics: commutative laws, and then associative laws, distributive laws. So this is what we want to discover. So do you think there is associativity involved here as well? The answer is yes. So what does it mean? It means that if I have 3 prepositions, and it doesn't matter how should I group them. So P and with the result of Q and R is the same as if I write the first 2 in the pair of brackets, if I prioritize the first and over the second and. They are equivalent. Again, the proof goes through the table, but there is nothing weird about it. So if you don't mind, let us ignore that, skip that. So then, of course, this is also the same. So this is associative, yes? P or Q or R, yes? It is important to understand commutativity and associativity. For example, so what is the meaning of this? So can I simply write this? Is it ambiguous or not? I can write it. This is not ambiguous because even though I have 2 conjunctions involved, it doesn't matter if I do this one first or that one first. According to associativity, they are the same. For example, if I say in the exam 2 plus 3 plus 4, 5, people immediately answer the 10, because it doesn't matter if you add 2 and 3 first and get 5, and add 5 to 5, you get 10, or you add 3 and 5 first, it becomes 8, and add 2 to 8, it becomes 10. But if I do the same thing with this, then you should complain, because division is not associative. So I cannot ask you this in the exam to calculate the number, because it matters. If you do this one first, 2 over 3, and then divide it by 5, so the answer becomes 2 over 15. But if you do that one first, it becomes 3 over 5, and if you do this division, it becomes 10 over 3, and you see that they are not equal. So when I say associative, it is relieving. It doesn't matter which way I group them, because it is not ambiguous. If you want, you can remove all the pair of brackets. So that is the deep meaning of associativity, yes? Okay, what next? What do you think we will talk? So commutativity, associativity, and distributivity are always coming together to check if this is true or false. So number 8, associativity, so distributivity. When I have distributivity, I have 2 operations, not 1 operation. So let me talk a little bit about distributivity. For example, I have an operation of multiplication and operation of addition. Yes, I say multiplication is distributive over addition. What does it mean? It means that if A is a real number, B and C are real numbers. If I add B and C together and it becomes a new number, and then I multiply A by the result, it becomes the same as if I distribute multiplication over this pair of brackets by writing A dot B plus A dot C. Yes. And of course, in principle, I have to put a pair of brackets around them, but because we have a convention in order, meaning that multiplication by convention has priority over addition, so I really don't put the pair of brackets around them. Yes? So this means that multiplication is distributive over addition. Do you think the other way around is also true? Is addition distributive over multiplication? If it was, what does it mean? What does it mean? It means that I should be able to write A plus B times A plus C. Which is, of course, nonsense in numbers. Yes? So this is true. This is not true in general. So we say that multiplication is distributive over addition, but addition is not distributive over multiplication. Okay? But here, we have number 8. We want to check if this is true or false. So you see, I have a conjunction and disjunction. I want to see if it is true that conjunction is distributive over disjunction. But I just want you to tell me what happens if it is. Then we evaluate if it is really true or false. So, what happens? P and Q, then or P and R. Okay? And then P or Q and R, if it is true, it should be what? P or Q and P or R. Okay, it turns out both of them are true. But the proof is, I hope that this is trivial for you now. It is long, so you have to set up a table of 8 rows, construct the left side, construct the right side, and compare the last columns. The columns corresponding to the left side and the right side. And they will be identical, so you need to trust me on that. And of course, don't take anything for granted. You can check it yourself, but this is a very simple exercise. But it turns out both of them are true. Okay, so this is not like that. Okay, so any one of these operations is distributive on the other operation as well.
Didn't this have a name?
Boolean algebra. Yeah. I don't remember exactly the pronunciation. Boolean algebra. I don't know if they write it like this. Anyway. So, But from left to right, it is called distribution. But from right to left, that's also possible, because if they are equivalent, it doesn't matter. Sometimes this is given, we need this, we distribute. Sometimes this is given, we need this. We factor out. Yes? So I'm just saying that I'm factoring out P and out. If I factor P and out, from this one Q is left, or from that one R is left. And because I have commutativity, so it doesn't matter if it is R and P, still I can factor P and out, either from the left or from the right. So it doesn't matter because I have commutativity involved as well. Okay, but thing important I want to emphasize here. So if I have P and Q or R, so be careful. Sorry, let me write P or Q. So be careful. If you want to have distributivity, you have to have two different operations, not the same. Okay? So that is more or less the same thing. I have and here, I have or there, and then I have P and Q. Of course, here I have three different prepositions. Here I have two different prepositions, one P and Q. So one of them is repeating itself. Can I use distribution here? Yes, of course I can do that. So if let us do the distribution, what happens? What should I write? I should write P and P, or I should write P and Q. Yes? But what can I write P and P? This is the algebra of prepositions now. Is there something I can write for P and P? Yes, we have it on the board. P and P is the second law, idempotent law. So it becomes P. So this becomes P or P and Q. So I was able to show that this is what is equivalent to this one. It is not wrong, but I can do better. These are called absorption laws. Yes? What does it mean? It means that whenever you want to use distribution law, check if one of them is repeated. Because if one of them is repeated, if you do distribution law, you will go in a circular argument. Yes, if I start distributing this again, I go back to itself. If you don't believe, let us do that. So I would say P or P, and then I would say and P or Q. But P or P is again idempotent law, so it becomes P and P or Q. So of course any preposition is equivalent to itself. So it will not take us to a very good destination. We will actually fall in loops. Okay, so, but my claim is that if whenever that is a distribution law, but one component is repeated, the answer is absorbed into that repeated one by writing it just P. We want to understand that. And then of course there are two of them. So P or P and Q is again equivalent to P. I want to discuss a little bit about the proof of this absorption law. Of course, one proof is, as always, using the table. So I take the table and I prove that one. So for example, let us do it quickly here. So I have P, I have Q, I have P or Q, yes? And then I have the left-hand side. The right-hand side is already here, yes? So this is T, T, F, F, and this is T, F, T, F. This becomes T, T, T and F. So this is, I need to add these two, yes? So this is T, this is T, this is F, and this is F. Now compare this one with this one, they are identical, yes? Because P is T, T, F, F. The right-hand side is T, T, F, F. So they are also identical. So this is always the case, but can I have a little bit better proof for this by using algebra? Okay. For example, let us start from here. P and P or Q is equivalent to what? Do you have any idea? This proof is completely valid, but if I want to do it in a better way, do you see how can I continue? know why this beeping is coming. Oh, it's finished. Okay. Write this P in a way that there is a disjunction involved. Because I want to make, this is P or, I want to make a P or here so that I can factor P or out by distribution law. Okay, so P or P is not useful. We can do that. It is not wrong. You said P or P instead of P. That's quite okay because P or P, idempotent law, is equal to P, is equivalent to P. So that's not wrong to write it if I continue and copy and pasting the left. Okay, so then what happens? You are right. I have P or, and this is and. So that is the right-hand side of the distribution law. So I am allowed to pull it out. Yes, you are right. I pull it out. What happens? It becomes P and Q. So you proved something true. This is really true. P and P or Q is indeed this one, but that is not what I want. So this is not a wrong proof. What you have done is correct, but this is not useful for the purpose of this problem. Okay, so that's not working. So what should I do next? Again, the strategy is the same. I want to write P in a way that P or is involved. Okay, idempotent law didn't work. What do you think I will do? Number 4. No, sorry. Oh, I think I missed something. Yes, I think there are some laws that I have to write them there. Okay, so because I want to write this in a way P or. Okay, so there are some laws that I don't know, for some reason I haven't written them down. So let me ask you this question. So P or this. Is it in my list? Unfortunately, I think I have forgotten that, put it in my list. I have to fix it. Oh, might be, yes, it is in my list, but, so this is not in my list, unfortunately. So the other one was in my list. So here, first of all, let us double check that one. Do you agree this is true? Yes, P and a contradiction is always a contradiction. P or a tautology is a tautology. But what can I write here with P or a contradiction? It's always P. Yes, is that understandable? Yes, because if P is true, then true or false is true, which is P. If P is false, false or false is false, which is P again. So I forgot to write them, sorry. So can you tell me another equivalence for this? P and tautology is equivalent to P. So actually this means that contradiction is an identity for this operation. It doesn't change the proposition. And tautology is an identity for that operation. It does not change that. Yes, why I call it identity, because you can compare it with 1 or 0. For example, 0 is the identity element for which operation? 0 is the identity element for addition, because any number added to 0, it will be the number itself. And if I ask you what is the identity element for multiplication, it becomes 1, because any number multiplied by 1 is the number itself. So in that sense, I would say that the contradiction is the identity element for disjunction, and tautology is the identity element for conjunction. I don't know. So these are called identity laws. So so in my writings, I have these two, but not these two, okay? But anyway. Okay, so instead of P, I can write P or contradiction, and then I can write and, copy and paste the left. the rest. Okay, can I use distribution law? Yes, but in the factory form. Yes, I can factor P or out, P or out. From here, a contradiction is left, and from here, and is left, and from here, Q is left. Yes? I have to put equivalent. And then what can I do here? Is there something I can write for this? A contradiction and Q, regardless of the truth value for Q, because this is conjunction with contradiction, it's a contradiction. So it becomes P or a contradiction. But what is P or a contradiction? It's P. Yes? So that's a better proof. That's a better proof for the absorption law here. If I want to prove this absorption law, you can do it as a practice yourself. Either you can do it like the table, or you can do it algebraically. Very similar ideas there. I will leave it as an exercise. Okay, there are other very important rules that I want to list here. So in principle, it should be 10, and this would be 11, but let me continue numbering the same. So 10. These are the De Morgan laws. De Morgan laws is that if you have P and Q and you want to negate this, okay? If you want to negate a conjunction, you can negate the components, but you have to change this to disjunction. Yes, so this is equivalent to saying that not P or not Q. And then I have also this negation of P or Q. The negation of a disjunction is the negation of the first one, negation of the second one, but disjunction will turn into a conjunction. Again, the proof is not hard by the table, so I will leave this as an exercise, but it is important you really convince yourself that this is indeed true. So, one idea in mathematical logic is that there are two fundamental operations. One of them is negation and one of them is and. Some books say that negation and or, okay? What does it mean? It means that if you give me negation and this and, I will be able to construct other things. For example, using these operations, can you construct, so can you write this disjunction as a conjunction? My goal is to show you that if you have, for example, if you want to write a program for a computer, you really don't need to teach the computer about or. You don't need to teach computer about a conditional. You don't need to teach the computer about biconditional. So if you have these operations, if your computer recognizes what is the meaning of these two, then you can program the computer understands or this and that based on these two operations. Okay, so can you tell me how do you define P or Q if you have only these operations granted to you?
P and Q and
No, use De Morgan's law here. So you would write negation of P and negation of Q and then negate the whole statement. So it becomes this. Am I right? Because according to De Morgan's law here, this negation goes for the first one and goes for the second one, but the price that you have to pay is to change a conjunction to disjunction. So if I ask you to simplify the right-hand side, what do? You say that this is negation of P, negation of Q, but this will become or based on De Morgan's law. But negation of negation is the double negation, so this becomes equivalent to P or Q. So this means that or can be written in terms of Q. Or can be written in terms of and negation. But the next theorem that is not trivial, and I want you to memorize it, is not that easy to remember, is how can I write this in terms of these two symbols? Okay. Now, you don't need to only use these two. You can also bring or in here, because if you already know how to write or in terms of these two operations. So the next theorem that I want you to know is this. Is any conditional, this is very important, simple but important, is equivalent to the negation of the first one or the second one itself. So if 2 is even, then its square is even. This is equivalent to saying that either 2 is not even or its square is even. Yes? If you think they are equivalent. Okay? I hope that you can understand it. You need to convince yourself that it is indeed true, but the proof is just how? How can I prove it? The table. So that's the only way that I can do it. But that is one of those extremely important ones. Okay? So if I want to prove it, let us just do it quickly. So I have P and Q. I have the conditional P and Q. If P then Q, I have not P, and then I can finish. So I can say that this is T, T, F, F. This is T, F, T, F, and this is T, T. This is F, and this is T, this is T. Not P is F, F, T, T. And then I have it here, P or not P or Q. Not P or Q, so I have the disjunction between these two. So this becomes T, this becomes T, this becomes F, this becomes T, and this becomes T. Yes, and now I compare this one with that one, they are identical. So that's the proof. Okay, but this is one of those cases, might be it is not that trivial, but I want you to memorize this one. Okay, what is the consequence of this one? If I ask you to find the negation of a conditional, what is the negation of the conditional? So you see, if 2 is even, so let me write like this. If x is even, of course this is not a statement, but you can consider it like that. If x is even, then x squared is even. Yes? If I want to read it like this, how should I read it? Either x is not even or x squared is even. It's a little bit strange. That's why I'm saying that it is better to remember this. But can you negate it without me telling you how to do it? This is not the case that if x is even, then x squared is even.
In a sentence or just?
Yeah, in a sentence. So, of course, if I ask you to negate this, you can start with the trick, but this is not the case. This is not the case that if x is even, then x squared is even, means, yes?
If x squared is odd, then x is odd.
No. That is what we call contrapositive. This is not the negation. That's exactly equivalent to this one. Negation is exactly the opposite. So just intuitively, that's why I'm saying that it is sometimes useful to study them systematically. So think about it. If x is even, then x squared is even. This is not the case that if x is even, then x squared is even, means so let me write it. This is not the case that if x is even, then x squared is even. means what?
If x squared, no, if x is
There is no if involved.
okay.
That's the whole point. The negation of a conditional is not a conditional. If x is not if, this is not the case that if x is even, then x squared is even, means that x is even, but x squared is not even. So that is the negation of that statement. So it's not a conditional. And that is easily understandable from here. What do you think I will write here now? So it's important to know this rule by heart. Okay? The negation of a conditional is equal to what? P and negation of Q. So the negation of this one is actually a conjunction. Okay? And why this is true, of course, again, whenever I ask you why, you can refer me to the table. But what is the wiser way to do it? The Morgan's law combined with this law. Yes? Because if this one is equivalent to this one, so the negation of that one is equivalent to negation of this one. But the negation of a disjunction, according to this rule, is the negation of the first one, which is the double negation formula, which gives me P. Disjunction will transform into a conjunction, and this one will also be negated. So these are important, very important laws. We use them all the time, and I'm sure that you know it by heart. It isn't, if I just start doing number theory, algebra, or whatever, if I'm using it, so you will understand me, okay? But if I want to write it systematically, so these two laws are extremely important, and one of them is exactly what you said, and that is the contrapositive law. These are called conditional laws. Okay, contrapositive law, what does it mean? So, number 12, if I have a conditional, do you remember, if I just interchange these two, this is not equivalent to this one, yes? What was the name of this, do you remember? If I give you a conditional, and then I write another conditional in which the role of these two is interchanged, then what do you say? This is called the converse. I want you to know these names, so the converse of that. And it is not the case that the converse conditional is equivalent to the conditional. So this is a common mistake usually, but don't take this. This is not in general equivalent to this. But there is another law which is also extremely important, and it's the basis of the proof by contradiction, is the contrapositive law. So the contrapositive of this, if I ask you to write the contrapositive, okay, I should write not Q. If not Q, then not P. This is what we call contrapositive. So the PDF file is below the video, so you can just download it later yourself for the spelling and everything. But this is called the contrapositive of this conditional. And then these two are equivalent. And that is called contrapositive law. So be careful. These three rules are extremely important ones. So you see, this is, by the way, proof by contradiction. Yes. For example, if I say that if n is even, then n squared is even. Okay? So then n squared is even. What is the converse? So first of all, is it true or false in number theory? Let us say n is a natural number. And it claims that whenever n is even, its square is even. Is it true or false? It's true. Whenever I have. Okay, what is the counterpart? What is the converse? The converse tells you that if n squared is even, then as n is even. It might be true or false. It turns out to be true as well. Okay, but if I ask you, but if you prove this, you cannot say that because I proved this, so if n squared is even, then n is even. Okay, so for example, in the exam, might be I ask you to prove this, you prove this, and in the second question you see this. You cannot say that I proved it in the previous question because they are not equivalent. P, if P then Q is not equivalent to Q and P, so there it needs another proof. Okay, because it might be true or might be false. But if I ask you, can you write the contrapositive of the first conditional? How do you write it? If not Q, then not P. So how do you write the contrapositive of the first statement? If n squared is not even, let me write it like that, you are right. Then what? Then n is not even. So these two are equivalent according to this law. Yes? So it doesn't matter. If you have proven this, it means that you have the proof of this one as well. But these two are not the same. So how can I prove this? Again, the same answer, the table, or here we have the alternative. So how can I do that? Let me start from the right-hand side. Right-hand side is not Q. If not Q, then not P. Okay? Whenever you want to use the algebra to prove things, it is better to get rid of conditional. So what can I write? Do you remember the formula for the conditional? If I have a conditional, I change the arrow to disjunction, but the price that I have to pay is to negate the first one and keep the second one intact. So what can I do here? I can take the negation of the first one or keep the second one intact. Okay? But negation of Q is what? Negation of the negation is Q or not P. But I can use commutativity, so it becomes not P or Q. But not P or Q is on the board, is equivalent to what? If P then Q. Yes? Is that right? Yeah. And then I will give you one law and then we have a rest. The last one is called the biconditional law. And the logic is good. So for example, can I write P and Q, if P then Q only in terms of these two? Yes? Can you help me to write it? So you see, not, I give you not, I give you and. We were able to write P or Q in terms of these two operations only by using De Morgan's law. Yes? Now my question is that, can you do the same thing for P if P then Q? Yes, it becomes what? Not P or Q, but we already learned what to do with or. So what should I write? I should write negation of P and not Q. Do you agree? So I was able to write this only in terms of not and. So those are more fundamental than the other ones. And now this last law is biconditional law. So can you write something for this? P if and only if Q. Yes, biconditional law means that P is a sufficient condition for Q and the other way around. So this means that this is if P then Q and Q if Q then P. This is called biconditional law. Okay, so I want you to know this by heart as well, but this is very trivial. I think the things that are not trivial, at least at the first glance or sight, so you need to remember these rules. The De Morgan law, these are not something. So you have to work on them to send them to your memory. I think it's important. Again, I don't want to prove this, but if you want to prove it, you can use the table to prove it yourself. But then I want to answer this question. Can you write this conditional, biconditional, only in terms of these two operations? Again, the answer is yes. So what can I write? For if P then Q, I can write this. So it becomes negation of P and negation of Q. And then I would write this and then negation of Q and negation of P, something like that. So you see that if I grant you these two operations, you will be able to write all the other ones in terms of only these two. Yes? Okay, so I think it's good to have a rest here, and then we start practicing a little bit about this. The next lesson I will talk about working with these laws. I hope that you have them in your memory. Yes? Yeah. Yes, thank you.